we were doing side channel attacks in this course, and we were attacking real crypto systems, right? So far, I think we've attacked together 3 crypto systems, actually 2.5. So does anybody remember which crypto systems we attacked using side channel attacks so far? Okay, already you're right. We attacked RSA. To be more specific, we attacked Montgomery left to right RSA using a tiny side channel. And we also attacked AES. Okay, we attacked AES. We attacked AES. Actually, I promised you that we would know how to attack AES using simple power analysis by analyzing the trace using template attacks. And actually, the third one, it's like, do you remember the first one that we attacked? What was actually it's not a crypto system, but it was password entry. We attacked using timing. Okay. So if we recall, let's try to compare the 2 attacks which we did all the way from the beginning to the end, RSA and AES. So the RSA crypto system, we did simple power analysis for RSA as well, but I'm not going to cover it right now. Let's talk about simple power analysis of AES and the template attack on AES, and comparing it to the timing attack on RSA and Montgomery. So here are the 2 in a very, very schematic view. So on the top, we have our setup for RSA. So what was our side channel? Can anybody tell me in the chat? While I drink this beautiful, delicious vitamin shake, what was the side channel we used to attack Montgomery left to right RSA? I can give you a hint. It's right here. What kind of side channel did we use? Thank you, Ilya. We used the timing attack. We used timing. So what did we do as attackers? We had a system under attack. This is a system, and we sent it queries. How many queries did we send it? Yeah, we sent it many queries, as much as we wanted. We sent them many queries to the system, and out of each query, we chose the input. We gave an input. What did we collect? What did we collect? We gave an input, and we collected trace. What was inside the trace? What did we measure? Let me look at the figure here. I'm spoon feeding you, and this. Yeah. We measured the time it took for the device on the test to do the RSA. Yeah, we measured the time, and from that we tried to deduce whether there was not a subtraction. Okay, we measured the time. This is what we had in our test. Okay, so we did many measurements, and each measurement we got the time. So the first question I can give you is, if you can recall, how could we justify this setup where we could have many timing measurements, and we could we had as many measurements as we want, and we could save the time each one took. So there were actually 3 settings I discussed. Can anybody remember? So one of them already says yes, if we have access to the device of the test, that's one. Sagi, wait with the template attack. We're not there yet. So what was the motivation? How could we justify doing this timing attack on RSA? So the first one was the device under possession. The second one, does anybody remember? Yeah, this is, so Oren, you're saying, why did we get the key out of it? But I'm saying, I'm going to the system architect, and I'm saying, listen, we're in big trouble. If an attacker can send a query to our device many times and measure the time, then the attacker can get out the key. So in which situations is this justified for an attacker to do? So one of them says, I have access to the card, as well. So I'll just tell you. The other one is, I am using a VM or a cloud service provider. I'm using a VM, or I am using a terminal system where I am sharing the same hardware with the victim because of all sorts of cloud setups or virtual machine setups or stuff like that. Okay. For an example, maybe I have okay, maybe I have a system which is isolating secure and insecure services using software, and the software is running on the same hardware, so I can measure timing. So this is the second setting. Does anybody remember the third setting? I will tell you the third setting. I need to get on with the course. This is when we have a cloud, a network service, which we can just send queries to over the network as many times as we want. And this is something which is very, very justifiable. So I can try logging in to a remote service, and as long as it's not doing some kind of anomaly detection and seeing that I'm accessing it many times, this is justifiable. So this is RSA attack. And now one last question I have for you. If I was an attacker doing this attack, and imagine that you're writing now a program that does this attack. What would be the data structure you would use to store your traces? So this is the traces. Would it be, so I'm not asking you to say hash table, thank you. So what do you get out of every attempt? What do you store? You store the timing. So the timing, what is the size of the timing? This is an array of size 1. It's a scalar, right? You get the number of milliseconds or microseconds it takes you to perform the operation. Okay? So, so if I do 1,000 attempts, I'm going to have a data storage of time 1,000 numpy array. I'm going to have a data structure of size 1,000, so 1,000 traces, and each trace will have the time, which is a scalar. So I'm going to have an array, a vector of 1,000 times 1. 1,000 attempts. Each attempt got me one measurement, one timing measurement. So are we good so far? Did we understand like the setting and data structure for the RSA timing? Really, really good. Okay, very nice to hear that everybody understood. Okay, and now let us return to it's not different from, yes, it's not different from hardware 1, exactly. In hardware 1, it's a crypto system. It's not a crypto system, it's a secure system. And again, we did many, many attempts, and we stored, and we also needed to store what was our query, the plain text, and the time associated with that plain text. So we have, let's say, 1,000 plain text and 1,000 times. Now, let's talk about our attack on AES, which I promised you it's possible, and I spent an hour talking to you about why it's possible. So I added this little graphic that will help you understand it better. So in our attack on AES, our template attack, we began with a very, very sensitive and long power measurement of the device under test when it was doing computation on, let's say, on a known plain text. It was encrypting this plain text with an unknown key. And then I told you that there is this magical being, this magical machine called a decoder that you build using template methods. And this decoder can output the state byte in each one of these rounds. So it's going to look at the trace, and it's going to output the state byte of the value of the state byte in the middle. And as I told you, you can't really get the values. You can only get the, what can you get? You can get the Hamming weights. Indeed, you can get the Hamming weights. So you can get the Hamming weights of all of the bytes of the state. And in fact, you can get more than that because of the way AES is implemented. But so the theory here is that you have a very big trace, and you have a magical machine that looks at parts of the trace and outputs the Hamming weight. And then you get the Hamming weights. What do you do next? What do you do next? I have the Hamming weights. What do I do next? So if I have, once I have the Hamming weights, I have in fact an equation set. I'm not telling you where the decoders come from. Well, you're saying you didn't tell us how do I get the right points. There is a way to find the right points. I'm just saying that there are right points. Okay. I'm just trying to say, you know what? Let's pause and discuss this a little. Does anybody need convincing? So who believes me here that this decoder only needs to look at a small amount of this very, very long trace? So who believes me and doesn't need convincing that this decoder the decoder is trying to find the Hamming weight of 1 byte of add key only needs to look at this little part and not at the whole thing. So who believes me? Maybe I should convince you. Okay. Okay. I'll tell you about CPA today, God willing. I'll get to it. I'll try to do it. So why does this decoder, which I didn't tell you what it does, but this decoder exists. It's basically a machine learning classifier, as Stjepan told you last week, which gets as input a lot of features. This traces a whole set of features, but it actually only looks at 10 or 15 or 20 of these features, and all the rest it ignores, and then it classifies what is the Hamming weight of. So why is it doing that? Why does it only need to look at a small part of this long trace? The answer is that if you look at the evolution of the state over time, there is in the past, before this calculation happened, in the past, there was nothing about this byte was appearing in the trace because the device under test didn't actually process it yet. So we can throw away all of these bits in the past, all of these traces. They can't be relevant to, let's say, I want to find out the Hamming weight of the subbytes. I can't look at the past. Now, if you look at the future, why can we discard the future? Well, we can discard the future because we assume that this is a very, very good crypto system that mixes all of the bytes of the state and the key so well that our decoder doesn't have any good insights, any simple way of recovering the value of the states if it looks like one round ahead, because everything is mixed up so well. So in essence, you want to find out the Hamming weight of, let's say, 1 byte of the subbytes operation, you're going to look at a very, very small part of the trace. Now, how do we find this part? And what do we do to find this part? One approach is template attacks, and you have everything you need to learn about it independently. Unfortunately, I won't have time to teach you this here. Why can we discard the past? Yes, so would this be Alex? No, it's Dimitri. Okay, so now I also know Alex has declared that he has a nice blue-colored picture. Right. We don't know. I'm not. So listen, Oren, I'm not telling you now how to construct this decoder. How do you construct a decoder? That's a task. You can read about it. But I'm trying to convince you that doesn't matter how you build this decoder. It could be machine learning algorithm. It could be Bayesian. It could be whatever. It doesn't have to look at this entire trace from the beginning to the end. It's only looking at a very, very small segment of the trace. This small segment of the trace is dependent on this, let's say, 1 byte of subbytes, and the rest of the trace is not dependent. Or the dependency in the past is not dependent. In the future, the dependency is so complex that this decoder is finding the Hamming weight of the subbytes from here is equivalent to breaking the crypto system and then simulating it once again from one value of the byte, and that's really, really nice. If you can do that, that's really awesome. But it's not something that we can do if the crypto system is built well, and AES is built very, very well. Right.